Hello students, today we'll be looking into the part 2 of the electrochemistry that we had learned in our previous class. So in today's class we will be learning about the electrode potential and the factors affecting the electrode potential, and then we will be learning about the standard hydrogen electrode, or also known as normal hydrogen electrode. Its working functions and limitations we will study. So first of all, what is electrode potential? Electrode potential, which is also represented by the capital letter E, is defined as the tendency of an electrode. Electrode is a metal strip that is dipped in the electrolytic solutions. Electrolytic solutions in an electrolytic vessel. So it is the tendency of an electrode to gain or lose electrons when it is in contact with its own ions. So one condition for the electrode potential to be developed is that electrode has to be kept in the solution containing its own ions. We cannot keep the zinc electrode in the copper 2 plus ion solutions, or we cannot keep the copper electrode in the zinc 2 plus ion solutions. If it is done so, then we cannot get the electrode potential. So therefore, another definition gives you a very clear picture that it is the potential difference between the metal electrode and a solution containing its own ion. So the basic condition here is it should have the solution containing its own ions. When a metal zinc, for example, when a metal zinc, this is a zinc plate, negatively charged zinc plate. Zinc plate, how it is negatively charged, we will discuss here. When a zinc metal plate is placed in a solution containing one of its sort, that is zinc sulfate, then metal becomes negatively charged due to accumulation of electrons on the surface of the metal. So what happens? The two electrons will be lost, and as a result Zn2 plus will be released into the solutions, and two electrons will get accumulated in the metal strip of the zinc plate. As a result, due to accumulation of the negatively charged electrons, the zinc plate develops negative charge. Negatively charged. Now, the positive charge that is Zn2 plus ions that is available in the solutions will cluster around the surface. They will come around the surface. So all these plus ions that you see is the zinc 2 plus ions around the negatively charged. Now, as a result, one is negatively charged, one is positively charged. As a result, electric layer is developed. This electric layer developed is because of the zinc 2 plus ion. So as a result of this development of electric layer here, there develops a potential difference between the metal and the solution containing its ions. So that is how the electric potential is different, and zinc electric potential develops because of the formation of layer. Now we'll see the copper one. In the case of copper ions from the electrolyte, you have the copper electrode dipped in a solution containing the copper sulfate. You can see copper and copper here. So copper 2 plus ion from the electrolyte, so from here electrolyte moves to the cathode here, because all the way the two electrons will be coming. So it moves to the cathode and it will gain the two electrons, and then it itself gets deposited in the copper metal. So in the process, what happens? All the copper 2 plus ions that is available in the electrolytic solutions will cluster around. They will get accumulated around the zinc plate, ready to receive the two electrons, so that they can, on receiving, they can form the neutral copper electrode. But in the process, what happens when they are accumulating around the copper plate? Simultaneously, sulfate ions, that is the negatively charged ions, will surround the zinc plate, because this is positively charged plate. Unlike in the zinc, you can say zinc is negatively charged plate, and therefore positively charged zinc will surround and form the electrical layer. As a result, the potential difference is developed. Same thing happens here. Copper 2 plus ions in the solutions will move to the copper plate ready to receive the two electrons flowing from the wire towards the zinc plate. So as a result, they accumulate here, and then the copper plate becomes positively charged. Now towards the positively charged, this positive charge will be clustered by the negatively charged sulfate ions, and as a result, potential difference is created. Potential difference is created between the electrode, that is the copper electrode, and the ions in the solution that is surrounding it. Factors affecting electrode potential. So there are 1, 2, 3 factors that affects the electrode potential. Nature of metal electrode. So different metals, you know that different metals have a different tendency to lose or gain or accept electrons. Those metals which lose electrons easily will have higher oxidation potential. And those metals which can easily accept electrons will have higher reduction potential. Reduction means to gain electrons, oxidation means to lose electrons. So those who are having the higher tendency to lose electrons will have a higher oxidation potential, and those metals which can easily accept electrons will have higher reduction potential. Concentration of metal ions in solution, this is important. Magnitude of electrode potential. How much is the electrode potential? Higher, lower of metal depends on the concentration of ions in solution. Now when we talk about concentration of metal ion present in the solution, the concentration of metal ion present in the solution will be directly proportional to the reduction potential of given electrode. Higher the reduction potential of the given electrode, more the concentration of metal ion present in the solution, higher the reduction potential of the given electrode. However, slightly difference when it comes to oxidation potential of the given electrode. Reduction potential usually happens in the cathode and oxidation potential happens in the anode. Concentration of metal ion is inversely proportional to the oxidation potential of given electrode. So that means when the concentration of metal ion is very high, oxidation potential of given electrode decreases, or when the concentration of metal ion is very low, oxidation potential of given electrode increases that time. So if we are connecting and trying to find out the EMF of the cells, in order to increase the EMF of the galvanic cell, suppose we have connected the Daniell cell, that is the galvanic cell. Now if we want to increase the concentration of, if we increase the concentration of metal ion in reduction half cell, suppose we are increasing the concentration in the reduction half cell and decrease the concentration of ions in the oxidation half cell, then we will see the increase in the EMF of galvanic cell. So therefore, in order to increase the EMF of galvanic cell, what do you have to do? You have to increase the concentration of metal ion that is present in the reduction half cell, and simultaneously you have to decrease the concentration of ions in the oxidation half cell. Temperature. Change in temperature affects the equilibrium between ions and pure metal. Increase in temperature shifts the equilibrium from left to right, making the electrode potential more negative, vice versa. Now comes the standard hydrogen electrode or normal hydrogen electrode. So standard hydrogen electrode to compare and find out the correct electrode potential of the different metals. So what is SHE? SHE stands for standard hydrogen electrode, or NHE stands for normal hydrogen electrode. SHE, this is the diagram of SHE. SHE is an electrode when hydrogen gas at 1 atmospheric pressure, here I have 1 bar, but actually it is 1 atmospheric pressure, 1 atm, at 1 atmospheric pressure is in contact with hydrogen ions. So you have the hydrogen ions present here of 1 molar concentration at 25 degrees Celsius. So H plus ion at 1 molar concentration at a room temperature of 25 degrees Celsius. So you have to maintain 3 things here: atmospheric pressure, that is 1 atmospheric pressure, concentration 1 molar, and room temperature 25 degrees Celsius. So therefore, when an electrode of hydrogen at 1 atmospheric pressure is in contact with the hydrogen ion of 1 molar concentration at 25 degrees Celsius, then it is called SHE or NHE. The standard value of SHE is considered as 0 volt. So there will be no volt there. So it will be considered as 0 volt. SHE is therefore used as a reference electrode in order to determine the electrode potential of any given electrode which is in standard conditions. So you have to maintain the standard temperature, pressure, and then connect with the other metal electrode in order to find their potential value. So how do we construct the SHE? The construction of SHE is not very simple, so therefore it is hardly experimented. You have to first prepare 1 mole HCl solution, and that is taken in a glass vessel, maintained at a temperature of 25 degrees Celsius. Then a thin platinum wire, this is a platinum sheet, thin platinum wire. From here you can see thin platinum wire having a flat platinum black is inserted. You have to insert this one and dipped in HCl solution through a glass test tube. At the side of the glass test tube, a small opening is present. You can see the small opening here, through which hydrogen gas at 1 atmospheric pressure is continuously passed into the tube. The platinum does not take part in the electrochemical reaction, and it just serves as only the site where electrons are transferred. So it is just for the mode of absorption of hydrogen gas. So therefore it will not take part in the chemical reaction. So you will not see any platinum metal taking part in the chemical reactions. Now, working or measurement of electrode potential using the SHE. The hydrogen that is passed through the opening here, maintained at 1 atmospheric pressure, will undergo oxidation. As a result, it produces 2H plus ion plus 2 electron. Then hydrogen ion that is present in the solution will undergo reduction reaction. It will gain the 2 electron that is lost by the 2 hydrogen again, and from the hydrogen gas. And that hydrogen gas is bubble out from here, you can see. The oxidation or reduction potential of SHE is considered as 0.0 volt. That's we have already talked about that one. It can be used as an oxidation half cell, or it can be used as a reduction half cell. It mean to say that SHE, depending upon the electrode that is connected to it, it can be either used as an oxidation half cell or reduction half cell, depending on the types of electrode whose potential is to be measured or determined. If the given electrode acts as an anode, suppose you take a zinc, the zinc will act as an anode, then in return the SHE will act as a cathode. For example, copper electrode will act as a cathode, so in turn SHE will be behaving as a anode there. So let us look into two examples both for the zinc and the copper. So when SHE is connected to half cell consisting of zinc electrode which is dipped in zinc sulfate solution, in that case the electrode will behave as anode, that is, a zinc electrode will behave as anode and SHE will behave as cathode. Therefore, the 2 electrons will flow from the zinc electrode to the SHE when it is connected. The 2 electrons that is released during the oxidation reaction in the oxidation half cell, the 2 electrons will be flowing from the zinc electrode to the SHE, and the 2H plus from the solution will combine with the 2 electrons coming from the zinc and form the hydrogen gas, which appears in the form of bubbles. And this is the net reaction. If we cancel this 2 electron, you will have zinc plus 2H plus Zn2 plus S2. Now looking at this one, we can also write the cell notations of the cell reaction from the cell reaction. Now next, when SHE is connected to half cell consisting of copper electrode dipped in copper sulfate solution, the electrode will behave as a cathode and SHE will behave as an anode. Therefore the two electrons will flow from SHE to the copper electrode, and 2H plus from the solution will combine to form H2 gas, which appears in the form of bubbles again. Oxidation half cell reaction, hydrogen, in this case SHE is reacting as an anode. So 2H plus 2 electron will be released. Copper is acting as a cathode. It will gain the electrons and form copper. The net reaction will be the two electrons will be cancelled, and these 2 H plus ions will combine to form the hydrogen gas, which will be in the form of bubbles. Limitation: it is very difficult to set up the experiment and maintain the concentration of HCl solution at 1 molar and pressure of gas at 1 atmosphere. It is very difficult to maintain. So it is one limitation. The hydrogen gas is highly explosive and inflammable, so therefore it is again another limitations while constructing the SHA. Platinum black contaminates very easily due to adsorption of impurities, and moreover platinum is one of the expensive metal. Relationship between the oxidation potential and reduction potential. When you are calculating the electromotive force EMF of electrochemical cell, that is the E naught cell, using this formula is very important. E naught reduction at cathode minus E naught reduction at anode. An electrode at which oxidation takes place acts as an anode and has a negative value for its standard reduction potential. And similarly, an electrode at which the reduction occurs acts as a cathode and has a positive value of its standard reduction electrode potential. This is the explanation of that we have seen in the case of the zinc that is connected with the this metal can be taken as a zinc or it can be taken as a copper. So here in this case, since metal is acting as anode, so this is a zinc here. Okay, this is a zinc. So you can say zinc is forming Zn2 plus ion and 2 electron, and this is Zn plus 2H plus ions forming Zn2 plus and the hydrogen gas. And you can find out the E naught cell of the reactions as well. Now in the similar way you can also do for the copper and write the cell reaction. This is the general formula of the reaction that is happening with the SHE. Thank you. We'll continue the next sessions in the third part of the electrochemistry.